Hello, today I will walk you through a Java-based artificial neural network project that classifies the iris dataset using custom feed-forward networks trained with backpropagation. The iris dataset is a well-known dataset in machine learning and contains 150 flower samples with four features: sepal length, sepal width, petal length, and petal width. Each flower belongs to one of the three classes: Iris setosa, Iris versicolor, or Iris virginici. The goal of this assignment is to build the three neural network architectures, which are namely ANN1, a three-layer network with three hidden neurons; ANN2, a three-layer network with six hidden neurons; and ANN3, a four-layer network with two hidden layers of 5 and 7 neurons. Then we will compare their performance in terms of training and testing accuracy and the training time. The project is implemented using Java Swing for the GUI and custom code for the ANN itself. Let's break it down. The main class is Iris ANN classifier, which extends JFrame to create the application window and displays a table comparing the three ANN models. First, we load the iris.data file using a buffer reader. Each line of data has four numeric inputs and a class label. We convert these into double arrays for inputs and one hard-coded int arrays for targets, like this. And then we split the data into training and testing sets. The first 25 samples of each class goes into training and the remaining 25 into testing. This gives us 75 training and 75 testing samples. We initialize the three ANN instances right here with the specified architectures we discussed before, and each model is trained using our custom ANN class for 500 epochs with a learning rate of 0.1. And after the training, we evaluate each model on both training and testing datasets and log their accuracy and training time in a comparison table. The AAN class handles the neural network logic. The constructor initializes layers, weights, and biases. The train method applies forward propagation and back propagation for a number of epochs. The feed forward then computes the activations layer by layer using the sigmoid function below, and backpropagate calculates deltas and updates weights and biases accordingly. Finally, evaluate runs predictions and calculates the accuracy. And this implementation uses vanilla backpropagation with sigmoid activations and stochastic gradient descent. Now let's run the application and see the output. As the app launches, it automatically loads the data, trains all three modules, and displays the results in a table. You will see the accuracy and time complexity of all three ANNs, and you can observe how deeply and wider networks generally achieve better accuracy, although they take longer to train. ANN3 often yields the highest accuracy. For the summary, we built and compared three different ANN architectures. We used the IRIS dataset, which is perfect for classification tasks due to its well-balanced and clean structure. The best performing model in terms of accuracy was the deeper network with two hidden layers, ANN3, but it also required more training and time. So this project demonstrates how architecture complexity impacts the performance in ANNs. It also shows the value of writing our own training logic from scratch. It helps solidify how forward and back propagation work under the hood. Thanks for watching. I hope this gave you a clear understanding of how ANNs can classify real-world data like iris. If you have any questions, feel free to